is to illustrate how you can calculate the electric field from the potential using this relationship that the electric field is the negative gradient of the potential. In the example, we have two charges placed along the x-axis at negative a and at plus a, and a point P which is a distance x along the x-axis and y along the y-axis, that is to say it represents any point in the xy plane. The potential at P due to the two charges is then written as kq over r1, where r1 is the distance from the charge on the left, plus kq over r2, where r2 is the distance from the charge on the right. If I put those distances in on this figure, this is r1, this is r2. These distances can be written in terms of where the charges are located and the coordinates of point P. So if I were to look at this right angle triangle, r1 is equal to the square root of this distance, which is a plus x. r1 is equal to a plus x squared plus y squared, square root. r2 likewise depends on this distance from the x coordinate of point P, and this is then going to be a minus x, given that charge q is a distance a along the x-axis. So r2 then is square root of a minus x squared plus y squared. Putting these into the formula for V, we get V is equal to kq over square root of a plus x squared plus y squared due to the charge on the left, and kq over square root of a minus x squared plus y squared square root due to the charge on the right. What we want now is to define the electric field as the negative gradient of the potential. You recall that the definition of the gradient is the directional derivative of the function relative to all three directions. Let us write this generally in three dimensions as the partial derivative of v with respect to x in the x direction, the partial v with respect to y in the y direction, the partial derivative of v with respect to z in the z direction, where I hat, j hat, k hat are the unit vectors in the x, y, and z direction respectively. Now, in this particular example, which is where the two charges and the point P are on the xy plane, the partial derivative of v with respect to z is 0 because the potential function has no z dependence. Let me also remind you that the definition of the partial derivative, let's say the partial derivative of v with respect to x, is the derivative of a function which is both a function of x and y, but taken while the second variable y is kept constant. Let us now calculate these partial derivatives. So this expression tells us now that Ex, the x component of the electric field, is the negative of the partial derivative of v with respect to x, and the y component of the electric field is the negative partial derivative of v with respect to y. The partial derivative of v with respect to x is the partial derivative of the expression, which has two terms. This is due to the charge on the left, and this is due to the charge on the right. When we take the partial derivative of both these terms, you see that the function of x is under the radical in the denominator of both expressions. So it's really taking the partial derivative of a plus x squared plus y squared to the negative 1/2. When we take that partial derivative, we are going to get a term which goes as negative 1/2. That negative sign which comes from the derivative will cancel the negative sign here. So what we will get is something that looks like negative of negative 1/2 kq of a plus x squared plus y squared. Instead of negative 1/2, it's negative 1/2 minus 1, so negative 3/2. So we can write that as a plus x squared plus y squared to the 3/2. But then you have to take the derivative of the expression under the radical, and that's going to be 2 times a plus x. The partial derivative with respect to x of the second term is going to give us something very similar, but when we take the derivative of the term that's under the radical, we'll get an additional negative sign. So this is going to give us now absorbing all the negative signs, what we get, and cancelling these factors of 2, what we get is dq and that's the x component of the electric field. We can do something very similar with the y component of the electric field, which is the partial derivative of this function v, which is in the square brackets here, with respect to y. It will look very similar to what we have relative to x. The only difference will be when we take the derivative of the term under the radical, we don't pick up a negative sign for the second term because the dependence on y for both the terms in the sum is identical. Little calculation will show that now we will get something that looks very similar, except that the sign of the second term is the same as the sign of the first term. So this is a plus rather than a minus as in the first case. Also, what we have in the numerator is a y, because when we are taking the partial derivative with respect to y, we will get, when we take the derivative of the term under the radical in the expression for v, we will get 2 times y, which will cancel the negative 1/2 we get from taking the derivative of the term under the radical. So this is Ex and Ey, and if we put these together, we finally get that the electric field just looks like kq a plus x I hat plus yj hat. So now I'm going to collect the terms that have the same denominators. But when you look at this expression, what you notice is that this is exactly what you would have obtained had you used Coulomb's law and the principle of superposition for these two charges. Let me remind you how this diagram looked. There was charge Q at negative A and 0, and a charge Q at positive A and 0, and we were calculating the field they produce at a general point P, which is a distance x along the x-axis and y along the y-axis. So the field due to charge Q would point this way, and the field due to the charge on the right Q would point in this direction. So the field due to the charge on the left would have a positive x component and a positive y component. The field due to the charge on the right would have a negative x component and a positive y component, which is exactly what you see in these expressions over here. The field due to the charge on the left has a positive x component and a positive y component, and the field due to the charge on the right has a negative x component and a positive right component. And the y components of both these charges is identical. The x components, however, are different because the charge on the right is closer, so it would have a larger x component.